All right, guys, we're going to go ahead and get started. Today, we will be going over related rates. First of all, I would like to avoid the issue that we had last week. Could somebody say something so I know that I can hear your audio?
Hi.
Cool. Thank you, guys. All right. So, like I said, we're going to be going over related rates this week. And that's going to build off of the chain rule and implicit differentiation, which we went over last week. So to start, I wanted to give you guys a second to ask any questions if you have any about implicit differentiation or the chain rule, because those are going to be the two big concepts that we're going to be using today. And going forward, we'll obviously keep working with those. But anyways, does anybody have any questions? No? Okay, cool. Well, I will share my screen and we will get started. So today we're not going to be using the whole recitation period. The questions that Dr. Zlecki sent, I wrote them all up for us. And as it turned out for first recitation, we only ended up using about 35 minutes of the time. So that being said, if at any point you would like to interrupt me to ask a question, I will stop after every question to see if there are any and if there's anything that's unclear. But if you'd like to stop me, we definitely have time to take asides and to break down what how these problems, how you're going to go through them. So with the related rate problems, they like a lot of the problems that we do in this course, you can break them down into steps and it's going to be kind of the same for every single one. The first step, and down here in this blurb down here, I break it down into the steps in the way that I do it every time. So we'll go through the steps and it might feel a little tedious maybe when it comes to the diagrams that I draw because they are simpler for these problems, but we will do larger story problems, possibly. I don't think it'll be on this exam. It'll probably be on the third unit exam. And we will use, or I will teach it using the same sort of structure. And so to implement that and sort of set the pattern early on, I'm going to use that today. And you'll see what that looks like in just a second. So these related rate problems, the majority of the legwork comes in breaking down the problem and all the facts that are given to you in these sentences, and then putting all of those puzzle pieces, as I like to call them, in one place, then finding an adjoining equation that will relate all the variables and constants that you're given in the story problem. And then from there, it's implicit differentiation and probably plugging in. So we'll start by reading the question. Each side of a square is increasing at a rate of 6 centimeters per second. At what rate is the area of the square increasing when the area of the square is 16 centimeters squared? So the first thing that I always do is I'll draw out a diagram. So for these problems today, the diagrams are going to be pretty simple. But we're given a square and we're going to assign the variable x as the length of the square, which is going to be changing. So first piece of information I write down, because we are asked about the area of the square, this is going to be our adjoining equation that brings together the variables that we need. And as you're going through these problems, this might be the last thing that you put down for your puzzle pieces, because the first things that I would have written down are these. So dx dt, we're told that the square each side of the square is increasing at a rate of 6 centimeters per second. And since we have denoted the side length of this square as x, we say that with respect to time, x is increasing at 6 centimeters per second. And we will come to find that the sign of these derivatives are important. If it said that it was decreasing, then the rate would be -6 centimeters per second. Although they might not write -6 centimeters in the story problem, if they say decreasing, you're expected to infer that and to represent the proper sign in these problems because it will change your answer. And then the other piece of information that we have, well, this is what we're looking for. I always write down the final puzzle piece because with these problems, you're given a whole bunch of information at the beginning and you might not know what the problem is going to look like. So if, like last week when we were doing implicit differentiation, we ask you to do implicit differentiation, it's going to look pretty much the same every single time. And you can sort of guess ahead of time what you're going to be writing out. So you're going to do the implicit differentiation, you're going to isolate all of the y prime terms, and then you're going to end up factoring out and dividing so that you get y prime by itself. You can picture that ahead of time. With these problems, they're sometimes a little bit different from problem to problem. And so I think it's important not only to have all of your puzzle pieces in one place so that it's a little bit clearer, but to have specifically what you're looking for. And you don't have to denote it in any particular way. There's no structure that will get you more or less credit in terms of like the order in which you do things. But this is my recommendation to you, is to make it very explicit to yourself what it is that you're looking for. And so then finally, we also have that we're given the area of the square is equal to 16 centimeters. Oftentimes you'll have to do a small conversion, because so the rate that we are given is given in terms of X. Area is also in terms of X, but we're going to need to plug in X eventually. And so we have to figure out what X is. And by the area formula, we can find that the X, or the side value of a square that has an area of 16, its side is going to be 4 centimeters. And so this is, when I say the legwork, this is the legwork. This is the setting up of the problem. It's breaking down the different aspects of the story problem, so converting it from a verbal form into a symbolic form. And specifically, I really recommend that you put down what it is you're looking for. And then what it is you're looking for is usually going to be your indicator as to what your adjoining equation is going to be. And an adjoining equation isn't necessarily, that's not a term that you'll see in the textbook. That's just kind of what I call it. It's the equation that's going to sum up, it's going to bring together all of the pieces of the puzzle that you're asked to use and help you to find your answer. Any questions on the setup of this problem thus far? No? Okay. So we are going to start with our equation, and we are going to, so now we've done the first step, we've done the diagram, and we've done the puzzle piecing. And so now we're going to go ahead and do our implicit differentiation. So using this equation, we differentiate implicitly, and we get that the dA dt, which is what area is, or how area is changing with respect to time, is equal to 2x times dx dt. And we do this by the power rule and also by implicit differentiation. And so when we look at this equation, a equals x squared, we dropped the 2 and reduced the power to 1. So first we regarded x squared as a variable, but we know that the side length is changing. And so it has its own rate of change. And so using implicit differentiation, we are also going to multiply that by dx dt. And from there, we're just going to plug in the values that we already have. You might not have had this value here, and you might not have, so when I was setting up this problem, you might have thought to yourself, well, how did she know to think ahead and to figure out what X is specifically? Why couldn't I have just plugged in A? You don't have to necessarily know this ahead of time. You could, a lot of students I would expect would just put A equals 16 centimeters and then go into the implicit differentiation. But once you get to this step, you're going to realize that you need to plug in X, and then you'll think back, okay, how am I going to figure out what X is? And it should be fairly simple because the dimensionality of a square is pretty straightforward, something we're familiar with from the beginning of our experience with trig. And so then it just becomes a simple plugging in problem. And our final answer is going to be 48 centimeters squared. Any questions on the implicit differentiation part of this problem? So one thing that I will say is that I wouldn't necessarily expect you to put the units next to every single one of these values when you plug in. That's not something I would take away credit for if you did not do, but you will be expected to give the proper final unit. And so if the assessing these units in your head is something that you don't think that you will be good at, then I would recommend that when you plug in these values, you put in the units so then you can visualize how they're multiplied and divided in order to figure out what the proper unit is, because you won't lose a ton of points, but I would say a minimum of 1 or 2 points if it were a story problem written out on an exam. You would lose if you did not give the proper units. And so, like I said, I've got a little blurb here talking about the few steps in terms of how you break them down. So the first thing I always do is draw the figure. For these particular problems are a little bit simpler and you can probably visualize it just fine, but I still always do it for myself because I think it's just easier. It gives you something tangible to attach all of this information to. Second thing being you put up the puzzle pieces. So if I probably should have written these in a different order. First would be you write in the given info. So you break down the problem and you take all the facts that are given to you, all of the rates, all of the values, all of that. You put that all down. Second, you would write down what you're looking for. So that's this dA dt. The question says, at what rate is the area of the square increasing when the area of the square is 16 centimeters squared? So that's going to be your end goal here. And then once you've got all of those pieces together, then you can start to think, okay, what equation am I going to use? And so then you would write down your adjoining equation, which in this case was A equals x squared. And so from there, you just do the implicit differentiation and you crank the problem out. If you set the problem up the correct way. And again, there's no specific structure that you're going to be expected to implement. But if you get all of your pieces in one place and you have this explicit reminder of what your end goal is, then it's kind of once you get started on the problem, it sort of guides you through it. It's a plug and chug at that point. So the setup, like I said, is where the majority of the legwork lies. And then once you get going on the implicit differentiation, more often than not, it just becomes take the derivative and then plug in, and then that's your answer.
I had a quick question.
Yep.
So like, I know this might be silly, but like, how do you usually find like what to use, like dy dx or dx or dy? You know what I mean? Like when you're finding the differentiation for
Okay.
like a
So
variable.
like in terms of these symbols here, how do I decide which one to use?
Yeah.
Okay, so dy dx is not something that we're going to use very often. You're typically used to seeing dx dy thus far in this class because more often than not, we've asked you to take the derivative of a function y that has variables x. And so that's why you're used to seeing dx dy. When we get into these story problems, the units aren't always going to be dx dy. And the reason that we know in this case that, so I'll start by saying I chose x as the side variable, or as the variable for the length of the side. You could have said s, you could have said something else. I chose x just because I don't know, that's just what I chose. But we are told, so if you look at this rate of change here, 6 centimeters per second, that's going to be your big indicator as to why it's dx dt. So we've got time on the bottom. So we're saying that this length here is changing with respect to time. So whatever you decide to assign, whichever variable you choose to assign for the length is going to go on top because that's what's changing. And then over what period of time, so with what variable it's changing with respect to is going to go on the bottom. So for this particular problem and for most problems, when you're given a rate like this, the units should match up sort of with your variables. Does that make sense?
Yeah, that definitely makes sense. Would it be possible that you're gonna go over like a implicit differentiation problem, like a complex one, to find the equation of a tangent line later this recitation? 'Cause I saw
Well,
something like that on the quiz homework, but I couldn't figure it out.
so we can definitely, after recitation, if you'd like to hang around, we can look at a problem if you've got some questions about that, but we don't have an equation of a tangent line problem lined up today for related rates. And in my experience, I don't think that we will have one of those.
All
But
right,
we can definitely take a look at those after recitation. We should definitely have time.
thank you.
Yeah. Any other questions on this one before we move on to the second one? Fantastic. All right. So the radius of a sphere is increasing at a rate of 4 millimeters per second. How fast is the volume increasing when the diameter is 80 millimeters? So again, I have a simple little diagram here just to visualize it for myself. First thing I write up is the increasing rate of 4 millimeters per second of the radius of the sphere. So I've assigned the radius, the variable r, and I'm told that it's changing with respect to seconds. And so we call it dr dt. And we're told that that is going to be equal to 4 millimeters per second. We are asked how fast the volume is increasing. So dv dt is our question mark here. And this is going to be a positive value. We should contextualize that ahead of time. And it's important once you get your answer to think to yourself, okay, conceptually, does it make sense that it should be increasing? Does it make sense that it should be decreasing? Is this value too large? Is it too small? Whatever it may be. And so the puzzle piecing ahead of time can kind of give you some guidance on that. Then we also are given that the diameter is equal to 80 millimeters, but we're given the rate of change of radius. So we're going to be doing this most likely in terms of r. This is similar to this step up here, where if it didn't occur to you right off the bat to break this down and put it in terms of r, that's fine. You could go back and like the problem would sort of guide you and suggest to you that you don't have it in the correct form. But since I was putting all my puzzle pieces in one place, we will reduce it, or we'll isolate r and get that it's equal to 40 millimeters. So now we think, okay, what's our adjoining equation? So we need to find the rate of change of volume. We know we're going to implicitly differentiate some sort of equation. So we're probably going to use the volume equation. And so we get that the volume is equal to 4/3 pi r cubed. That's a mistake. Go away, please. Pi r cubed. So I'll take an aside really quickly and just mention what sort of equations you should be familiar with, or I would recommend that as you go through these story problems, so all of the problems that we do today, the adjoining equations that I present, those you should be responsible for, and I would start sort of a running list. Problems that are presented to you in WebAssign. We won't do any problems with cones today, but you may see some of those. If you don't, then you don't have to expect to see it on the exam. But if it does come up in your WebAssign, I would write it down on that list of equations that we use. Um, that being said, in my meeting with Dr. Zalecki last week when we were discussing related rates, it sounds like we're going to be focusing more on triangles, squares, circles, and maybe their three-dimensional counterparts. So you should be familiar with the surface area and volume of spheres, cubes, not necessarily prisms. I wouldn't say triangular prisms, but you should be familiar with, so if we're doing a problem that has to do with a triangle, which we will do later on, you should know that the Pythagorean theorem is going to be the best adjoining, or is more often than not going to be the equation that you're going to use for that. So to sum up everything I've just said, all of the adjoining equations that we've done today, I would write a list of those. If there are any problems on WebAssign that use different equations that aren't presented today, I would add those to your list. But in general, surface area and volume are going to be the more complicated ones that you need to write down, because not many people have the volume equation for a sphere memorized. But when it comes to problems like the area of a square or even the volume of a cube, you can figure that out because it's fairly simple. So moving on to the actual calculus part of this problem. So we're going to differentiate the volume equation. We get that dV dt is equal to 2, which came from dropping, well, that shouldn't be 2, that should be 3. 3, which came from dropping that cubed variable, still multiplying by the 4/3, still multiplying by pi, and then we have r squared because we've reduced the power from 3 to 1. And then we're going to multiply by dr dt because the radius also has a rate of change. And so this is our power rule. This r squared and 3 term, though they're broken up, that's the power rule part. And then these are just the constants that we maintain. And then this is the implicit differentiation chain rule part. And so now the only thing that we don't have is dv dt. And so we can plug in r squared, or r into r squared and dr dt, and just plug and chug and find these values. And so, like we deduced from the problem earlier, we know that dr dt is going to be 4 millimeters per second. We put together that since the diameter is 80 millimeters, we know that diameter is the length across it. So the diameter would be from all the way across there all the way to here. The radius is going to be half of that, from the center to the outside. And so half of that would be 40 millimeters, which is plugged in there. And then that should be squared. And then we still have our 4/3 and our pi as our constants. And what it shakes out to be is 25,600 pi millimeters cubed per second. So again, the units are important. You got to double check your units for these problems. But I did just want to point out the fact that this pi is a part of this answer. That's perfectly fine. I'm not saying that I would take, so say I was grading a homework assignment and you gave me a decimal answer. You multiplied this 25,600 times 3.1415, whatever, and you gave me the decimal answer. I wouldn't take away points for that on a homework assignment. But if you're doing an exam and this exam is not open calculator and you give me a decimal answer, more likely than not, like most students aren't going to go through and do that multiplication. And so that would maybe be an indicator to me that you were using resources that you weren't supposed to. And so you may lose points for that. So what it boils down to is that it's easier just to multiply it out and just leave the pi in there. It's, again, this goes back to not simplifying it. Once you've done the calculus, there's no point simplifying it to the very simplest form unless you're asked to do so, because you're A, going to open yourself up to the possibility of more mistakes. And B, in this case, you may be indicating to the grader that you're using tools that you're not supposed to, say if it were on an exam. So having this pi variable, or not variable, symbol in here, that is a totally acceptable answer. Do we have any questions on this problem? Okay. Number 7, the radius of a spherical ball is increasing at a rate of 2 centimeters per minute. At what rate is the surface area of the ball increasing when the radius is 8 centimeters? So again, got my little diagram up there, which I just copy and pasted from the first one. First thing I write down is dRdt is equal to 2 centimeters per minute. So the radius of the spherical ball is increasing, so it's going to be positive 2 at a rate of 2 centimeters per minute. So the radius is going to be the length that is represented in centimeters, and then we're told that it's in minutes. We're just going to call it t. We're not concerned. So in the first problem, or the last problem, I should say, we did it in terms of seconds. This one we're doing in terms of minutes, and we don't have to concern ourselves very much. So both of these, what I'm trying to say, they're both called dRdt, but their units are different. And that's fine because we're just representing them. The only time you really have to concern yourself with whether or not the units are the same or different is if, for example, say they gave you a rate of 2 centimeters per minute, but then they said 8 millimeters. So you would want to make sure that everything is in like terms, but that's not something that I would expect on an exam. It might be a little something that's added in to spice up a homework problem, but just so that's on your radar and you can look out for that. So we write down, or I wrote down ds dt. What is that? So S is what I'm going to call the surface area. SA is what I always sort of write it out like this because again, this puzzle piece portion of the problem is meant to guide you. And so if there's something that represents the variables better to you, that's totally fine as long as you make it clear to the grader what you're saying. So if you want to say, okay, this is surface area, and I'm going to call this S, and it's equal to 4 pi r squared. Really what we care about is that you don't have DSA DT. We don't want two variables up here. That's not standard proper. I don't know. That's just not how we write it. So we've written down what we're looking for. And we're also writing down the constant we're given, which is r is equal to 8 centimeters. And since the radius is increasing, basically what they're saying is, so what the reason they give us this value because it's increasing and it's not going to stop increasing necessarily after it hits 8 centimeters, but we're asked to evaluate this problem at the moment at which r is equal to 8 centimeters. So that's why they give you this specific value. And so those are all our puzzle pieces. We've got our adjoining equation. And the reason that we know it's going to be surface area is because they ask us at what rate is the surface area changing when r is equal to 8 centimeters. And so then we go about our implicit differentiation. Again, we're going to use the power rule. So this 2 is going to drop down 2 times 4 times pi times r to the first because we've reduced the 1 in the power, or reduced to 1 in our power. And then again, multiplied by the implicit differentiation aspect of this derivative, which is dRdt, because we're told that the radius is changing. And so we have to include that rate of change in the greater rate of change that is ds dt. And so at this point, we've got all our values we need to plug in. We've got r, which is 8 centimeters, and we've got dRdt, which is 2 centimeters per minute. And so when we plug in, we get 128 pi centimeters squared per minute. And again, this is another example of where pi is, it's totally acceptable to have pi in your answer. In general, for this class, it will be totally acceptable to have pi as a part of your answer, especially when we get a little bit more into the trig problems going forward. Any questions on this one?
I have a question.
Sure.
So, are we going to be given like the equations for things like these, or do we have to memorize them? Like for
You will
surface
not be
area
given the
and
equations.
volume?
No. Which is why I recommend that you write, it's a good, very good question if I didn't make that clear before, but you will not be given the equations. This is the type of problem, this is the type of explanation you can expect. They're not going to say use the equation s is equal to 4 pi r squared. You'll have to deduce from the puzzle pieces what equation should be differentiated.
Okay, thank you.
Yep. Any other questions? Okay. I think we got 2 more. Yep. All right. The altitude of a triangle is increasing at a rate of 1 centimeter per minute, while the area of a triangle is increasing at a rate of 2 centimeters squared per minute. At what rate is the base of the triangle changing when the altitude is 10 centimeters and the area is 100 centimeters? So first thing I want to address is what the altitude is. If you don't remember from your trig now, or from your trig education, which is probably back in high school, or maybe you've taken some in college. But if you don't remember, an altitude is really just sort of this imaginary line that we use to represent the height of a triangle. And so we're going to go about this problem in terms of base and height, B and H. We're not going to use altitude, but you should be able to recognize. So it gives us the rate of change of the altitude, and that's going to end up looking like dH dt. So our adjoining equation, which again, I wish I would have written towards the end so that we could go through each step of all the facts you're supposed to pull from this problem. But we are asked about the, let's see, what part of the triangle? The area of the triangle is increasing at a rate of 2 centimeters squared per minute. So we're given area, and its area includes both base and height. And so we're going to be able to use the information that we're already given and find the information that we need from this equation. So we are also told that the altitude is increasing at a rate of 1 centimeter per minute. So like I said, I called the altitude h in this case. So dH dt is equal to 1 centimeter per minute, positive because it's increasing. We're going to want to find dB dt. Where is that? I guess I didn't write it down for this one. We're going to want to find dB dt. That's our end goal. So I'm going to write that down so I can remember to adjust that for when I send you guys this note via email later. We're also told that the area is increasing at a rate of 2 centimeters squared per second. And we're given the values at the instant at which we're supposed to be evaluating this problem. Given the values, h is equal to 10 centimeters and area is equal to 100 centimeters squared. So this might be something that we have to manipulate in the same way that we manipulated d equal to 2r and area equals 16, x equals 4 centimeters. This might be something that we do something similar with, which we will. But you don't necessarily have to know that off the bat, but just to sort of walk you through the thought process, because with all these problems, the more you do them, the more you tend to pick up on the pattern. And I feel like it's easier to navigate your way through the chaos when you can sort of maybe have some guesses, be a little bit preemptive about what you're going to do. But ultimately, the most important thing is that you know what you're looking for and that you've got the equation that's going to relate what you're looking for and what you already have. And so we're going to do our implicit differentiation on the area equation. So we get that dA dt is equal to 1/2. This constant affects both base and height. And so it's going to affect the derivative of both base and height. And since base and height are both changing, they're both functions. And so we're going to use the product rule to do this. So these are kind of flip-flopped, but it is the derivative of the first times the second plus the first times the derivative of the second. And that's how you find the derivative for this particular one. Any questions on how I differentiated the area equation in this case? Fantastic. Okay, so now I'm going to take an aside. Let's see. I'm going to take an aside, and at this point, that's the reason why I'm now going to be doing the conversion of a is equal to 100 centimeters squared is because I've found this derivative and I've done the differentiation step. And now I'm looking up at my puzzle pieces and I'm looking to see what I do have and what I don't have. So I have dA dt that's given as 2 centimeters squared per minute. 1/2, it's constant, don't have to worry about it. I don't have the base. I do have dH dt, 1 centimeter per minute. I do have h, 10 centimeters, and I'm looking for dB dt. The issue lies in that there are two variables here that I don't have. I don't have b and I don't have dB dt. So I've got to figure out a way to deduce b because I'm not going to be deducing dB dt. dB dt is going to be what I solve for because that's the end goal. I've got to find a way to figure out what b is from the information that I'm already given. And so that's where this area equation comes into play. And so we set the area 100 equal to 1/2 base times height. We find that 100 is equal to 5b and that b is equal to 20. I probably would have written centimeters here in retrospect. Again, I'm not, so this is kind of maybe a little bit more of a gray area. I'm not sure that I would take away points if you didn't put the units on this intermediate step here, but since you are finding a value, it would just be safer because I'm not going to be grading the entirety of the exam. Dr. Zalecki may have different thoughts on it, but if you're determining what the value is of a variable, it's probably going to be smart to assign its units at the same time. So moving on, we get to plug everything in at this point. So dA dt is equal to 2 times 1/2 times the base, which we figured out was 20 over here, times the rate of change of the height, which is 1, plus the height itself, and then times the rate of change of the base. So now the only thing that we have that we don't have the value of is dB dt, and that's exactly the way we want it to be. And at this point, it just becomes a problem of simple algebra. And we find that dB dt is going to be equal to negative 1.6 centimeters per minute. When it comes to an exam, I would be totally fine. Well, I mean, this is simple enough that you should be able to figure out what the decimal is, because this 4 minus 20 will be negative 16 divided by 10. But say you've got something a little bit more complicated, you could probably leave that in its fractional form and receive full credit. Any questions on this problem before we move on to the last one?
Wait, how did you get the derivative of dH over dt as 1 again?
So that was given to us in the context of the problem. So
Oh,
if
okay.
so the altitude is h, to reiterate.
Okay.
Yep, this first sentence here. Any other questions? Okay, last problem. So this problem is about a ladder sliding down a wall. This problem, it comes back time and time again every semester that I've taught. And so does so like for the spherical changing of radius problem. So for example, a snowball is melting. So those are two types of problems that you can pretty much expect on your exam. There may be one other type, but at least you've got maybe 2 out of the 3 that are going to be on your exam. I'm telling you for a fact that you should be able to do these ladder problems, and you should be able to do a sphere problem. So we'll dive into this one. The top of a ladder slides down a vertical wall at a rate of 0.15 meters per second. At the moment when the bottom of the ladder is 3 meters from the wall, it slides away from the wall at a rate of 0.2 meters per second. How long is the ladder? So this one, it's even more important. So I'll start with the diagram. I assigned the variables y and x because we've got a vertical wall and a horizontal floor. And to me, this kind of reminds me of a coordinate system. And so an x, y, and z often in 3-dimensional coordinates, those go together. And so I'm going to call the length of the ladder z, and then the x coordinate and y coordinate are going to represent the floor and the wall. So first thing that we're told is that the ladder slides down the vertical wall at a rate of 0.15 meters per second. And so what that tells us is that y is going to be decreasing. And if y is decreasing, dy dt is going to be negative. And so we get that dy dt is equal to negative 0.15 meters per second. So like I said, they're not always going to give you, it's not always going to be increasing or decreasing or positive or negative rate of change. You have to contextualize and figure out what the problem is actually telling you. So then the next thing we're going to write down is dx dt. So visualize this ladder sliding down, and as it does, the bottom of the ladder goes further and further away from the wall, and so x is increasing at a rate of 0.2 meters per second, which is given to us in the problem. Next, I write down that x is equal to 3 meters. So this is the instant at which we're asked to evaluate the problem. And finally, well, not finally, we want to find z. Finally, our adjoining equation, x squared plus y squared equals z squared, the Pythagorean theorem. So with the equations that you need to know, there's going to be a handful of equations that you've seen before and you can probably just pull up by memory. Then there's going to be an equation or a handful of equations like the surface area or the volume of a sphere or something like that you aren't necessarily all that familiar with and you may have to memorize. This is something that I would expect a lot of students to have in their back pocket. And so when you get a triangle problem like this should be your first thought. This is the first thing you should think about, unless it's say the area, then it would be 1/2 base times height like in the last problem. But still, those are two types of equations that we've been using maybe since we were in 4th grade, whatever it was. And so those aren't the ones that you should be using your mental effort for necessarily to memorize. I mean, if you don't have them memorized, if you couldn't drum this up from your prerequisite knowledge, then yes, you should. But the ones that I would maybe write down a few times to make sure that you've got ingrained in your brain are those more complicated equations. And so we've got all of our puzzle pieces here. We've got our end goal. We've got our diagram, which this is probably the most important problem that we do today. That is the diagram is the most important for this problem in particular, because the direction at which the ladder is moving changes the values of these derivatives. And so now that we've got all our puzzle pieces, we can go ahead and differentiate Pythagorean's theorem. So we get 2 times x times dx dt. So much like all of the other problems we've done, we're going to do the power rule and we're going to drop the 2. And so we've treated this x squared first as a variable. So in doing that, we've just applied the power rule like we would if it were y equals x squared. But we know that the length, or that the distance from the ladder's end and the wall, represented by x, is increasing. And so it has its own rate of change that affects the greater rate of change. And so we have to include that. And then same methodology here, we get 2 times y times dy dt and equal to 0. So this is an important part. If you remember back to implicit differentiation, say we were given x squared plus 2xy is equal to 4, that constant would be differentiated to 0. And then you would go, and then you would move things to the left side or the right side of the equal sign, because that constant is negligible when we're talking about its rate of change, because it does not change. And since this is a ladder, the ladder is not going to stretch, it's not going to shrink. The length of the ladder is going to be constant. And so it has a rate of change of 0. Any questions so far? Okay. So now, much like implicit differentiation, we're going to move stuff around. This is a little bit different in this case, though, because we're not seeking to combine y prime terms or to isolate them, but just to sort of like to call on some of the things we've already taught you. That's why it looks the way that it does here. That's why the derivative is going to be set equal to 0. Now, you could choose to keep it as 0 and to plug and chug until the end. Ultimately, you're going to be plugging in the values and you'll be able to deduce the answer quite simply after you've done the derivative or taken the derivative. And so we've got our x value, we've got dx dt, we've got dy dt, but we don't have y. So once again, we're going to have to do some sort of converting from the information that we're given in order to find out what y is, because y isn't the end goal, z is the end goal. And so Pythagorean's theorem is going to be what we use to find z. But y, we're going to have to use our context clues to figure out what that is as an intermediate step to find z. And so now we plug in what we do have. And I want to mention that it doesn't necessarily matter where the negatives are. They're going to end up canceling out regardless of whether or not you have them on the left or on the right, because I believe the book does it a little bit differently than I do. But the negatives, they'll shake out the way they need to shake out. You don't have to worry too much about them as long as you have them assigned correctly. And so then we get that y is equal to 4 meters. Like I said, you should probably put your units on so if we're defining what y is, we're going to define it with its unit. Even though this isn't necessarily the end product or this is the answer to the problem, I would still kind of cross my T's, dot my I's, and put the unit on that, on y as we're assigning it. And so now we've got everything that we need, basically, but this one has an extra step where you have to plug back into the original equation. So we have the x value, we have the y value at the instant that we're asked to evaluate this problem. And so then we're asked to find out what z is. And so we have this handy dandy equation where we can just plug those values in. We get 3 squared plus 4 squared is equal to 25. And then we get the special right triangle with lengths 3, 4, 5. And that's how you do this last problem. Any questions on this one? No? Okay. Well, we've still got some extra time. I'm going to stop sharing. If you have any questions, I see some questions in the chat. So where do the recordings of recitation go once this is over again? So if you look back in your email, I believe the subject is recitation links or something like that, LB 118 recitation links. You should be able to find an email wherein I give you the Zoom links and passwords for the morning recitation, the afternoon recitation, my office hours, and a YouTube page. And the recitation recordings are all uploaded to the YouTube page. Okay. At this point, that's pretty much everything that I've got for you guys. So you are free to leave unless you have questions or want to hang around and see what other students have to ask. Homework 2 has been graded. I'm not sure if the person who inputs the grades has put them into, no, I believe actually she has. So homework 2 grades are uploaded and you should have your grades for homework 3 by next Tuesday. All right, have a great week. I'll see you guys next Tuesday.
Thank you.
Bye.
Bye.
Thanks.
Yep.
I had a question.
Sure.
For like, I think it was number 7 on the one you did.
Okay, let me share my screen again. Number 7. Okay.
Yeah. So when you're like taking the derivative of like the 4 pi r squared, are you treating 4 pi like a constant? Is that way?
Exactly.
Like, okay, like both of them, or wouldn't just 4 be the constant, or are you treating like pi as the part of the constant?
Pi is also a constant. So since it's an irrational number, it's technically 3.141592, whatever. It's a very long repeating decimal. And so what you could do is you could multiply that. So it would shake out to be roughly 12, right? 12.4 or something like that. But we don't want to write that long repeating decimal. And it's more accurate to represent the irrational number with a symbol. And so these two together are the coefficient, but they're both constants, right? So that's a fair question, but you do treat them both as constants.
Okay. Okay. Thank you.
Yeah. All right. Who had a question at the beginning or earlier about a tangent line problem? Are you still hanging around? I guess not. Where is my Zoom? Where? Okay. All right. Any other questions?
I also had like a quick question about 21. Sorry.
Okay. No, that's totally fine. I couldn't get back. I couldn't find my Zoom page. So I just exited out of the screen sharing because I knew it would just kick me back to the Zoom. You said number 21?
Yeah.
Okay.
Can you explain the like the that step? Yeah, the one you're like, I still don't get
I
it.
had a feeling that that would be the one. Okay, so this is a simple product rule problem. The reason why it might be a little bit, I don't know if overwhelming is the right word, but there's a lot of symbols here that we're not used to seeing. And so basically what it is, so are you comfortable with this 1/2 being kicked out front since it's a constant?
Yeah.
Okay, so I should have flip-flopped these just based off of, so when I taught you guys how to do product rule, I told you to kind of do it the same every time in your head. So the derivative of the first times the second plus the first times the derivative of the second. I should have flip-flopped these because technically the first in this case is b. But so what it is the derivative of the first, db dt, times the second plus the first, b, times the derivative of the second. Does that make sense?
Oh, I see. Okay.
It's a little, it looks more complicated than it is, but it's just a product rule problem.
Oh, okay. Thank you.
Sure. I'm going to stop my share, see if anybody's still here. Oh, yep, 5 participants. All right, anybody else have any other questions?
Thank you. Bye.
Yeah, no problem, Munzer.
I guess I have like a I guess I have a general question. How do you know when to not touch the constant to leave it alone?
All right. So in general, let me pull up some examples so that we're all thinking of the same thing. In general, when you're taking the derivative of something, so this equation here has a constant out front and it interacts with these two functions, which are also, we're going to treat them as functions and we're going to treat them as variables when we take the derivative. But it has a constant that's interacting with it. And so this constant is going to affect the rate of change when we take this derivative here. We're going to, so with the one that was set equal to 0, where is that one? Here. So in this case, z is a constant, but it's not interacting with any other aspects of the derivative. It's independent. And so we're going to, when we take the derivative of this constant, it's just going to be 0 because it doesn't change the derivative of the functions that we're taking the derivative of. So those are kind of two examples of when you would include the constant and when you would, this isn't necessarily getting rid of it because technically the rate of change of a constant is 0. But does that answer your question?
Yeah, it does. So like if it's gonna affect the derivative, you keep it.
So like if it's touching other variables that you take the derivative of. This
Okay.
is a kind of a fluke. This is a weird one because it's still like we call this a variable. You know, it's a symbol that represents a value, but much like pi is just 3.14, and that pi symbol represents a value, but you still know to treat it as a constant.
Yep. All right. Thank you.
Yep.
Hi. I just
Hi.
have one more question about the equations and stuff.
Okay.
So can you like send a list of like what kind of equations we'd be using most of the time? Because I don't have like specific ones like memorized. Or are there like a certain like is there like a few certain equations that we might just need to use and that's it?
That's a good question. And that's something that I considered doing when I was writing my recitation note. And the reason I
Mhm.
hesitate to do that is just because I don't want to write a list and either put too much on it or too little. And then you guys do all of your studying based off of that. Because my understanding of this course is limited to what Dr. Zalecki asks me to present to you guys. And so when you guys do WebAssign, I don't know what you're doing. So I think it would suffice to write a list of just the equations that we've used today. But I will ask Dr. Zalecki, I'll email him and ask him if he can give me some guidance on that, because he's going to be the one who knows what's on the exam. And then I will relay that information to you. But I don't want to give you too much or too little, and then you study incorrectly based off of what I've given you.
Okay. Well, that's okay. Well, you can send me if he does tell you anything. Like
I'm sure he
it
will.
doesn't really matter to me if it's like
If it's too much.
if I need to memorize it. Yeah, that's not
Okay.
too much.
Sure. Then
All
I'll
right.
get you something. Sorry.
All right,
wait.
thank you.
Yeah, no problem. I'm sorry. I just don't see you. Whose name is this? Okay, Sarah.
Sarah.
All right, Sarah. No problem.
Thank you. Okay, bye.
Yeah. Can you also send me that list too?
Yeah, I'll send that to the whole class, but just in case I wanted to correspond with her specifically on that, but I'll make sure that you get it too.
All right. Thank you.
Yep, no problem.